Hi, my name is Dr. Rambabu. I am working as a assistant professor in the Department of Electronics and Communication Engineering. I am from B.V. Raj Institute of Technology, Narsapur. Here I am dealing with course called microprocessors and microcontrollers. Our today's topic is memory organization of 8086 microprocessor. Before we are going to talk about in detail things of memory organization of 8086 microprocessor, let's focus on learning objective of our today's topic. To understand the memory organization in 8086 microprocessor with the following subtopics. The first one is memory segmentation, next one memory addresses, physical memory organization, and next one is the programmer's model. All these things in our today's topic, here we are going to continue. Right, here in this memory organization of 8086 microprocessor, first we will talk about the memory of 8086 microprocessor. In 8086 microprocessor, totally 8086 contains 20 address lines. That means it contains 2 power 20 address lines. That is the 2 power 20. That is the memory space of the 8086 microprocessor. If you can convert the 2 power 20, that is the 10,48,576 memory locations are there. By using the size of the address bus, here we can able to calculate the total memory can be accessed by 8086 microprocessor. If you can convert this number into MBs, totally 8086 microprocessor can able to access totally 1 MB memory space. Here in our today's topic, how 8086 microprocessor is going to organize that 1 MB memory space for different operations. Those things here we are going to continue in our today's topic. First, let's talk about that is the memory segmentation part here. If you can check the total 1 MB memory space, the 1 MB memory space that is divided into totally 16 equivalent possible segments. The size of the each segment here it is the 64 KB. Here to access the data from the 64 KB of each segment, here we are going to use the two different addresses. One address is called the base address and next address is called the offset address. The size of the base address is 16 bits. The size of the offset address is 16 bits. Totally, by using some calculation, some physical memory calculation to get the 20-bit address, here we are going to use the different types of techniques. One of the memory technique here we are going to use to calculate the 20-bit address in the coming slides. Here the segment registers are here used to store the base address of the segment here. Here totally to access the data from each segment of 8086 microprocessor, here we are going to have some type of registers like segment registers and some type of registers like offset register. Here to store the base address of the segment, here we are going to use the register called that is the segment register. Usually, if you can combine that is the logical address size here we are showing with the 16 bits. The total 20-bit address here we are calling that as the physical address here. Next, here the totally 8086 microprocessor, here we are dividing into totally 16 segments. Out of 60 segments, only 4 segments are initialized. Those 4 segments are, one is the code segment, here we are calling in short form CS. Next one is the data segment, here we are calling in short form DS. Next one is the stack segment, in short form we are calling as the SS. ES is the extra segment here. Totally in our 8086 microprocessor, out of 16 segments, only 4 segments are initialized. Here we are remaining 12 segments are there. Here depending on our requirement, we are going to initialize these 12 segments also. How to access the data from these 4 segments, here we are going to explain, here we are going to learn from a table. Suppose if you can check, if you can call that is a code segment. To access the base address of this code segment, here we are going to use a register called that is the CS register. The size of the CS register here it is the 16 bits. To access the offset address, offset 16-bit address, to store the offset address, here we are going to use a register called IP, that is the instruction pointer. Similarly, to access the data from the data segment, here we are going to use a register called data segment. and to access the data from this data segment for the offset address. To store that, here we are going to use that register called SI, that is the source index. Similarly, to access the data from the extra segment, ES is the segment register and DI is the offset register. To access the data from the stack segment 16-bit register, or to store the base address, here we are going to use SS. And to store offset address, here we are using, sometimes we may use stack pointer, sometimes we may use the register called, that is the base pointer here. Here this slide shows the main memory segmentation of 8086 microprocessor. Here this total, this table here that shows this table that contains the totally 4 segments are initialized here. Those 4 segments are, this part shows the, that is the data segment, this part shows the code segment, this part shows the that is stack segment, and the next one is the extra segment. The size of this data segment, here it is the 64 KB. The size of the code segment is 64 KB. The size of the stack segment is 64 KB. The size of the extra segment is 64 KB. Here, out of 16 segments, only 4 segments are initialized. Here this particular address, this is the bottom or starting address of the data segment. This is the top or ending address of the data segment. Similarly, for this one is the base address of the code segment. This is the base address of the top address, that is the end address of the code segment. Next one is this is the base address of stack segment. Next one is the top address or end address of the stack segment. Similarly, last one shows, this one shows this is the base address or starting address of extra segment. This is the end address or top address of the extra segment here. Now, by using the next slide, here we are going to check how to calculate 20-bit physical address to access the data from these 4 segments here. Here, this slide shows the memory address generation. Here, mainly the memory address generation will be done by in our 8086 microprocessor, the unit called bus interface unit. This bus interface unit has a dedicated adder for determining the physical memory address, that is the 20 bits here. First, the offset 16-bit value. The offset address that first we are going to check. Next, here we are going to check that is the 16-bit base address by using the segment register. And here we are going to add a 0. Otherwise, we are going to shift all the bits to the left side for the 4 bits, or we may add 0. That 0 usually we can call as the hardwired 0. Finally, here we are going to, by using this offset address, at the same time the 16-bit address and plus added hardwired 0, we are going to add by using the adder in the bus interface unit. Finally, we are going to get a 20-bit physical address. Here, this slide shows how to calculate a physical address for a particular segment address. Here, the logical address here we are specifying with the 16-bit segment address. Here we are showing with the 16-bit offset address. Here this value A4FB shows the segment address. Usually we are storing this base address. We can call as the segment address or base address. We are storing in the segment register. And this 4872, this address here we are calling as the offset address. Usually we are storing this particular offset address in the offset register. How we are going to calculate a 20-bit physical address for the given this logic address? Here this A4FB is the segment address, and this one I already told you. Here we have to shift all the bits to the left side 4 times, or you can add, that is a 0, hardwired 0. This 0 here we are adding here, and we are going to add a offset address 4872 to the previous that is the base address plus added 0. And finally, after adding these two, we are going to get the A9822. This address here we are calling as the 20-bit physical address. To access the data from any location in the totally 10,48,576 memory location, by using this technique, we are going to access the data from the particular memory location. Here this operation, this calculation can be applicable for the all the segments like stack segment, data segment, code segment and extra segment. For each and every segment the operation is same. In the next slide we are going to check with we are going to take any one of the segment. Here we are going to check how to calculate this 20-bit address. This particular slide shows that totally this is the 64 KB of our code segment. In this 64 KB of the code segment, now we are going to check how to calculate the 20-bit address. That means how to access the data from the particular memory location. This is the starting address of the code segment. Here that particular starting address, this is the 34BA. Usually that is storing the default segment address for the base address register or segment register. To store the starting address of the code segment, here we are going to use a register called CS. CS is the code segment register which can hold, that is the starting address. And here the top address that shows the ending address of the segment here. Here I already told you this is the 3488. 3488 is the 16-bit address. Here to calculate 20-bit address, here we have to add a 0. Otherwise we may multiply with the into 10h hexadecimal number. And finally we are going to get the 20-bit. This is the starting address of the, or that is the starting address of the code segment. And this one is the ending address or top address of the code segment. Here in this particular slide, here we are going to calculate, here we are going to access the data from this particular memory location. To access this particular memory location, to access the data from this particular memory location, here we are going to use this particular that is the 20-bit address calculation. First we can check here, the CS stores the 16-bit starting address or base address. Here we are adding the 0 here, we are adding the 0. This 0 here we are calling, that is the hardwired 0. Plus we are going to add the offset address. Finally after adding, that is the 0 to our existing base address plus offset address, finally we are going to get the 20-bit physical address. This is the final 20-bit address. This is the 38AB4 is the 20-bit physical address. This one shows our 20-bit that is the physical address. Here actually this offset address, the starting address we are calling as the base address. The offset address nothing but here the distance between the starting memory location, our required memory location. Here this one is the 4214. 4214, here we are calling as the offset address. To hold that 4214 default register, here it is the IP instruction pointer, is our default pointer or index register. This is our physical address memory calculation. Next we are going to talk about our physical memory organization of 8086 microprocessor. Totally 8086 microprocessor, here it is having the 1 MB memory space. 1 MB memory space. To access the total 1 MB memory space at a time, usually this will take more time to access the data from the required memory location. For that, the total memory of 8086 microprocessor, the total 1 MB, that is divided into two banks. One bank is called the odd bank and next bank is called the even bank. That means all the even bank contains all the even addresses, and odd bank contains all the odd addresses. To access the data from the odd bank from 8086 microprocessor, here we are going to use the D8 to D15 of the data lines. So by using the D18 to D15 data lines, we are going to access the data from the odd bank. By using the D0 to D7 data lines, here we are going to access the data from the even bank here. Here suppose if you want to access the data from the totally 1 MB memory space, every time suppose if you are not organizing like even bank or odd bank, it will take more time to access the data. Every time whenever we are going to access the data from the required memory location, that has to check each and every memory, that has to check from the 0, 1, 2, 3, 4, 5, so that. Suppose if you want to check the data from the odd bank, at that time this is only going to check all the odd addresses only that going to check all odd memory locations only. Similarly, for example, whenever we are going to access the data from the even bank, that is going to check only all the even memory locations only. Usually we can able to reduce the time accessing from particular bank here. In that way, the memory is going to be organized for our 8086 microprocessor. Here, to select the odd bank, here we are going to use the one pin like BHE or bus high enable pin. We are making is the 0. We are making as 0. Here, similarly, to activate or so to select the even bank, here we are going to use the one of the address lines out of 20 address lines, that is A0. We are making with the 0. So by using A0 is equal to 0, here we are going to select or we are going to make enable the even bank for the operation. So this is our physical memory organization. The next slide, here we are going to check the programmer's model of 8086 microprocessor. Whenever the programmer is going to write a programming instruction, is going to program for the 8086 microprocessor, definitely he has to understand the total memory architecture of 8086 microprocessor. This particular slide shows the programmer's model of 8086 microprocessor. In programmer's view, definitely he has to understood what is where exactly, how much of memory 8086 microprocessor contain, and how the registers are going to be used to access the data from this total 1 MB memory space. Everything he must understand. Here, this particular thing here, this shows our 64 KB of extra segment. This slide shows the stack segment 64 KB. This one shows the data segment 64 KB. This one shows that is the 64 KB of the code. Definitely, he has to know how many segments are available, how many segments we have to initialize for the operation. To store all the data related thing, while we are operating with the 8086, to store the data, here we are going to use the segment called data segment. To store the code related things, that is just like our opcodes and everything, here we are going to use the code segment. To store our stack related temporary data, temporary operation, temporary values, here we are going to use the stack segment 64 KB. Similarly, this extra segment is the extension to this data segment. Here also we are going to store the extra segment. Just like the source to destination operation, for the type of operation we are going to use the data segment as for the source and extra segment for the destination here. Here, how to access the data from these 4 segments. For that, definitely programmers must know totally 8086 microprocessor is having the 14 total registers are there. Out of these 14, some registers are general purpose, some are pointer and index registers, some are segment registers are there, and flag register is there. Here this AX, BX, CX, DX, these are the 4 general purpose register. AX is the accumulator, BX is the base register, CX is the counter register, and DX is the data register. And a pointer and index register, this is the stack pointer, BP is the base pointer, SI is source index, and DI is our destination index. And at the same time, these 4 registers usually here we are using to store the offset address. And similarly, to store the base address of each and every these 4 segments, here we are going to store the base address of the code segment. Here we are going to use the 16-bit code segment register. To store the base address of the data segment, the DS is going to be used. To store the stack segment base address, the SS is going to be used. To store our 16-bit starting address, here we are going to use the ES is our extra segment register to hold the base address of this extra segment register here. Similarly, the instruction pointer is also going to be used as sometimes as our index and pointer register to hold the offset. That means stack pointer and base pointer, source index and destination index and instruction pointers are going to be used to store the offset address of these 4 segments here. Here, this one shows our programmer's model of 8086 microprocessor. Next, After learning all those things, memory segmentation, memory addresses, physical memory organization, at the same time programmer's model, finally that is the learning outcome here. By end of this module, students will have a solid understanding of the 808 microprocessor organization, including how memory is segmented, how the addresses are calculated, the structure of physical memory, and the use of various registers in the programmer's model to manipulate the memory. They will be able to use this knowledge to write and debug assembly language programs effectively, understanding the relationship between logical and physical memory in the 8086 microprocessor. This is about the memory organization of 8086 microprocessor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.